Precalculus. So we are starting a new chapter, and we're going to be working on trigonometric identities for this first section. And to start with, I want to introduce our toolkit. We will add some things to this toolkit, but we're going to try and keep it very simple. So some basic things that you're going to have memorized. By the way, I'd recommend making flashcards of these various formulas that I'm going to give you. So the first one is for tangent of theta. We know tangent of theta is sine theta over cosine from our work with the unit circle. We also need cotangent of theta. Cotangent is cosine over sine. Note that it's the reciprocal of tangent, sine over cosine, cosine over sine. We're going to need our reciprocal functions. So let's see, secant of theta is 1 over cosine. And cosecant of theta is 1 over sine. Okay, so we need to have these guys memorized. Like, you need them kind of the same speed as you know times 4 is 8. That's how quick you have to be able to rip these off. So tangent is sine over cosine. You've got to have it right there. One other formula you're going to need in your back pocket is cosine squared theta plus sine squared theta equals 1. This is the fundamental trig identity. It's sort of one of the most important ones. It comes from the unit circle. We talked about where it comes from today in class. If you are absent, make sure you ask me about it so I can show you where this comes from. It'll make more sense once I do. But for notes, just know that you have to have this memorized. So sine squared, if you ever see that combo, it always equals 1. All right, using this toolkit and some algebra, we're going to be simplifying some trig expressions. So if you got a problem, for example, one like cosine of x equals tan x times, or sorry, plus tan x times sine x, the very first thing that you're going to do is use these formulas from your toolkit to simplify anything you can here and to turn it into sines and cosines. So for instance, I see a tangent of x. I know tangent is sine x over cosine x. So I'm going to substitute there. Once I change things to sines and cosines, then it's just a matter of using algebra to simplify. So I look at the multiplication first. This sine x is over 1. And I know that when I multiply two fractions, I go top times top, bottom times bottom. So sine times sine is sine squared x, because something times itself is squared. Cosine of x times 1 is cosine of x. And now I have a fraction that I'm adding with something over here, and I know that to add two fractions, I need to get a common denominator. So to get a common denominator, I'm going to multiply top and bottom of this fraction, the numerator and the denominator, by cosine of x. Cosine times cosine is cosine squared. I already have my sine squared. And this is all over the common denominator of cosine of x, because they both have cosine for the denominator. Finally, I see cosine squared plus sine squared, and one of the formulas I have to have memorized is that cosine plus sine squared equals 1. You just have to, you have to have that memorized. You have to just know it. And so I see cosine plus sine squared, and I know, oh, well, that's equal to 1. So I can write 1 over cosine of x. And then 1 over cosine of x we know is equal to secant of x. So what we've just done through algebra is we've showed that this cosine of x plus tan times sine is equal to secant. We sort of just proved that this thing, or simplified it down, is equal to secant of x. Now the reason this matters is that when you guys go on to calculus, if you were to see something like this, cosine x plus tan x times sine x, having this in a calculus problem would involve a lot of work and a lot of effort. It would be far simpler to simplify it down with algebra and then use just secant of x in your calculus problem. You're going to have to do a lot less with the calculus next year, and so you're going to save yourself time and effort by being able to simplify these trig identities, which it's the whole reason we're doing this in pre-calc, because we're getting ready for calc. All right, so you change to sines and cosines, common denominators, a little substitution there, and we get it simplified down. This is our final answer, secant of x. Okay, let's try that one more time with just a slightly different example. So here, everything already is in sines and cosines, so it's just going to be a matter of getting a common denominator. Now let's see, to do that, I'd have to multiply both sides, top and bottom, here by 1 plus sine theta. And this side by cosine theta on top and bottom. And now I need to distribute my sine. Sine theta times 1 is sine theta. Sine times sine is sine squared theta. Cosine times cosine is cosine squared theta. And this is all over my common denominator, cosine theta times 1 plus sine theta. So that's, you know, kind of a tricky common denominator. That's not trivial. And then I look here, and now I'm looking for places where I can try to simplify. So what I see, and this should start jumping out at you, is sine squared plus cosine squared. And I know that that's equal to 1 from my toolkit. So I'm going to substitute, this guy right here is equal to 1. So I'm going to substitute a 1 in there. I still have this sine of theta up here. And this is over cosine theta times 1 plus sine of theta, right? And now I have sine of theta plus 1 and 1 plus sine of theta. By the commutative property, right? Commuting means we can go back and forth, we can switch them. So I can make this 1 plus sine theta, I could rewrite it. And so they're equal, which means I can reduce. Now when I reduce these, I'm left with a 1, because something divided by itself is 1. So I have 1 over cosine theta, which coincidentally is the same answer that we got above. That is not always going to happen. We end up with secant of theta. It is not the case that the answer will always be secant of theta, but it is interesting that in both situations we ended up with secant of theta, starting out with things that looked completely different, and both of them ended up in the same place. Kind of cool. All right, guys. Let's see. Let's just, for our sake of our notes, get the steps written down. So somewhere in your notes, write steps. So step number 1, the first thing that you're going to do on all of these problems is sub in sines and cosines wherever you can. Wherever, there's no extra E in there. So if you see a tangent, you're going to sub in sines and cosines. If you see a secant or a cosecant, you're going to sub in the appropriate sine or cosine. After that, you're going to be looking to simplify using PEMDAS, using order of operations. And some things that you might have to do. You might have to get a common denominator. You might have to distribute. You might have to substitute again. You may have to factor at some point to be able to reduce. You're going to have to play around. It's not always going to be the same. And one of the things that makes these problems tricky is that there's a lot of ways to skin a cat. There's a lot of different ways you can go to get through these problems. The last thing that you should do in these problems is check your answer. And a simple way that you can check your answer, a nice easy way, is to use your graphing calculator. So if I wanted to see for, let's say, example 1, if this really did equal secant, one of the ways that I could check it is I could take my graphing calculator and go into my y equals, okay, and plug in cosine of x plus tangent x times sine x. And then in my y2, I could plug secant, which I know is 1 over cosine, since there's no secant function button. Oops. 1 divided by cosine. Okay. And now if I have this in my y1, this in my y2, and they're really equal, then they should be equal at every data point in my table. So if I go to my xy table, notice these are giving me the same exact values all the way down my table. They match everywhere. And if I graph, I only get one graph. Oh, my window's all crazy. Second quit. Let's set the window zoom 6 for standard. interesting. I'm getting a weird straight line, and that seems wrong to me because I know secant should be U-shaped. I know I should be seeing like some U's here for secant because we've graphed secant by hand before. I think it's probably a mode problem. So I'm going to hit second quit, and I'm going to go into my mode. I'm in degrees right now, and when we did our graphing before by hand, we were graphing in radians. Really the only difference is the window, but if I go to radians and then I graph, I should see that sort of signature secant curve. There we go. So I'm getting my like U shape where it's going away from the axis and it has vertical asymptotes. Alright guys, that's it for notes. Make sure you check the blog. There will be a couple of problems for homework, and I will see you guys tomorrow. Have a good night.